When you feel good, your brain is releasing one of the happy chemicals, dopamine, serotonin, oxytocin, or endorphin. We want these good feelings all the time, but they are not meant to be on for no reason. They're designed to reward you with a good feeling when you do something good for your survival. Our brain defines survival in a quirky way, alas, which is why we all do quirky things to feel good. Our happy chemicals are inherited from earlier mammals, and we control them with brain structures that all mammals have in common. The mammal brain can't tell you in words why it turns on the chemicals because it doesn't process language. When you know what turns them on in animals, everything makes sense. Dopamine surges in a monkey when it sees a fruit it can reach. Each step closer to a reward stimulates more dopamine. But the joy and excitement of dopamine stops when you get what you seek because it has already done its job. Then you have to do more to get more. The dopamine spurts of your youth built neural pathways that tell you how to turn it on today. These pathways helped our ancestors survive in a harsh world, and today they help you find rewards in ways that worked for you before. You can build new dopamine pathways to turn it on in new ways, but it takes a lot of repetition. Serotonin, oxytocin, and endorphin have their own jobs to do. Each surge builds the neural pathway that tells you to expect more good feelings in the same way. Each spurt is so short that you always have to do more to get more. Our brain evolved to promote survival, not to make you feel good. Nothing is wrong with you. Your happy chemicals are not designed to be on all the time. Ups and downs are natural, but you can build new pathways to enjoy more happy chemicals in new and healthy ways. Find out all about it at the Inner Mammal Institute. We have plenty of free resources to help you make peace with your inner mammal.
How does the rewiring of brain circuits happen? Well, a couple of things. First, you get a stronger go for it signal. Go for what? Go for the addiction. You've wired together a bunch of nerve cells that are screaming, let's do that again. Let's repeat the addictive behavior. This simply adds to the cravings of the numbed reward circuitry. Think of our circuitry as a muscle. If you exercise more, it will grow stronger. But if you seldomly use the muscle, it will get weaker. The more you use the reward circuitry, satisfying the cravings, the stronger it gets. The second thing is your control circuit, which understands the consequences of your action, will also be weaker. These higher circuits know that drinking a bottle of whiskey or watching porn for 12 hours a day may not be the best idea. So, with an addiction, it's sort of like a tug of war, and the go for it circuit is winning. To understand addiction, we need to understand what changes, and that is nerve cells. I'm boring you with all this stuff about the synapse. Why do we care about the synapse? This gap between two nerve cells? Well, this is where all addictions occur. All addictions. Changes here in the synapse lead to a numbed pleasure response and rewiring of the brain. What we have right now, at the left and right, is the nerve cells communicating. The red round things are dopamine being released by the sending nerve cells, and they're sending it from other parts of the brain. Now, the receiving nerve cells notice this reward nerve cells and are receiving the message, so electricity flows along the nerve cells. The more electricity comes, the more dopamine is released. So if you look at the left one, you have a whole lot of dopamine because you have more impulses of electricity heading down the reward cell. This would give you a greater experience of excitement. It may be like heading towards orgasm. You're high. You don't want to stop. Let's look at the right cell. You can see there's hardly any dopamine being released. This could be after an orgasm, where you have no desire whatsoever. So the level of neurochemical or dopamine release equals the power of the message. From something like methamphetamine or cocaine, the power of the message or dopamine can be huge. Here we are again, looking at a synapse. Notice the receptors. So the key is that the receiving cell is able to hear the message through the receptors. As I said, The receptors are like ears, or some people say it's like little locks. And in this case, dopamine is the key that unlocks them. And when they're unlocked, the message continues along the receiving nerve cell. Now, if you look at this picture, the cell's normal number of receptors is full of dopamine. Here it's simplified to just 4. So a go signal is being transmitted to the receiving cell. You need all those receptors activated to properly hear the message. With addiction, changes occur with the number of receptors. If you look at this, you have the normal number of receptors. In other words, the receiving cell can hear the message. The reward circuitry can hear it. While in this case, the number is low. Only a couple. This is what happens in all addictions. The D2 receptor is the type of dopamine receptor that actually crashes. That may not be interesting, but I need to mention that. Now with overstimulation, the dopamine will overflow into the synapse. The receiving nerve cell says, enough, I can't handle all this dopamine. It's like someone screams at you and you cover your ears. Well, nerve cells accomplish this by getting rid of their dopamine receptors.